Okay, we're getting back online. And I think it should be much better now. Yes, we can now do screen sharing.
Yeah.
Okay, can you hear me?
Yeah.
Yeah, we can.
Yeah.
Okay, great. Okay, so 33 of us, let's wait for others to join in. And you should now see the yellow board, right?
Yes.
Yes.
Okay, let's continue. So, indeed, if to illustrate the point which I was discussing previously, if we have a certain vector which is a directed straight line segment, then we know that it will be exactly same vector if we move it to another initial point parallel to itself. So these are not two vectors. This is exactly same vector. But in the first case, a certain point, for example, initial point, belongs to it. In the second case, obviously, that point doesn't belong to it. And that's why we can't say whether a point belongs to a vector at all. So the vectors are not geometric objects. So what are the vectors in that case? And the correct answer would be, and it is much more useful in general, that vectors are elements of a vector space, of a linear vector space. Then, of course, the second question is, what is the linear vector space? We'll discuss this. So, vector, by definition, vector is an element of a linear vector space. And then, what is a linear vector space? Linear vector space, interestingly enough, is a set of vectors. Is a set of elements, more strictly speaking, called vectors. Well, if we stop here, it would be just a tautology, possessing the following properties. And now it becomes constructive, such as, let me denote my linear vector space by, for example, L is a linear vector space. And let, for example, X be a vector of this linear vector space. So X is a vector in this case. Let's say Y is a vector, also an element of this linear vector space. So, first of all, for elements of this vector space, we have an operation called addition. There is a defined operation called addition. So for all, we would say x, y, which belong to this linear vector space, we have a vector which is called x plus y, where plus is addition in our linear vector space. And also, for any vector x in our linear vector space, we have an operation of multiplying that vector by a real number. So we have x plus y also belongs to this linear vector space, and alpha x belongs to this linear vector space where alpha is a real number, any real number. So elements of this linear vector space called vectors admit operations of addition and multiplication by a real number. By the way, please note that we're not talking about multiplying vectors by vectors yet. Only adding the vectors with each other, adding up with each other and multiplying by a number. That's all for the moment. Multiplication of vector by vector can also be defined, but it will be introduced later. For the moment, it's only addition and multiplication by a number, two fundamental operations of a linear vector space. Okay, this is not all, and these two operations must satisfy a set of 8 axioms. 8 axioms of addition and multiplication in linear vector spaces. Okay, so the first axiom is the axiom of, what do I think? Commutativity. Commutativity of plus. Which simply means that x plus y is the same as y plus x. Okay? Then it is associativity of plus. Which means that x plus y, a certain vector, plus z, another vector, is the same as x plus y plus z. And for this reason, so addition does not depend on either order or grouping of vectors. We can always write a sum of 3 vectors as x plus y plus z, and it doesn't really matter in which order they are written, very much like for real numbers. Please note that currently I am using this notation x, y, and z to denote vectors. Later on, we will be using same notation to denote not vectors, but coordinates in a 3D space, and that will be different. For the moment, it is just convenient for me to denote vectors as x, y, z, and so on. Now, the third axiom is the existence of zero. There exists such a vector. I will denote it actually not by 0, but by theta. And let me here use the theta notation. There exists a vector theta in our vector space such that for all x, we would have x plus theta equal to what?
X.
Equals to x, yes. So this theta plays a role of a zero element in our linear vector space. Okay. Now, what else? If we have a zero, then we have the inverse negated vector. So the fourth axiom, for any x which belongs to our linear vector space. By the way, I think that you are familiar with the property existence and universality. This symbol means there exists. This symbol means for all. Existence quantum and for all quantum. You should be familiar with them, are you?
Yes, we are.
Yes.
It was mentioned on the mathematical analysis lecture.
Great. Okay. So for any x or for all x which belong to our linear vector space L, for any x, there is another vector which we will interestingly call minus x, such that minus x plus x equals to what?
Zero.
Theta, which plays the role of zero. Minus x plus x equals to theta. Okay, so we got those four axioms about addition, basically. Now we have a group of axioms about multiplication. So the fifth axiom is associativity of multiplication by a real number, which means that for any alpha and beta being real numbers, and for any x which belongs to our linear vector space, we can say that alpha multiplied by beta x is, interestingly enough, same as alpha beta x. And then, of course, so this is an axiom, by the way. If we do not postulate this as an axiom, there is absolutely no way to derive it. It is just given. This is an axiom. But if this axiom holds, then we can continue as an immediate consequence, because real numbers really commute in multiplication, then obviously we can write it as beta alpha times x, and therefore this is equal to beta times alpha x. And this allows us to write it always without any brackets, just as alpha beta x, where alpha and beta are real numbers, x is a vector. Okay, that's associativity of multiplication. Number 6 is an axiom which states about multiplication that 1x, where 1 is a real number, x is an element of our vector space, 1x is obviously equal to x. But again, this cannot be derived from any other axioms. This needs to be postulated as a fixed axiom of a linear vector space. 1x equals to x. Okay?
Excuse me.
Okay.
Here we assume one is the element of the real numbers.
Yes, one is treated as a real number. It is not a vector. Let me say it explicitly. So one is just one which belongs to the set of real numbers. X belongs to our linear vector space. 1x equals to x. And so there are two axioms related to multiplication. And finally, we have two axioms which connect multiplication and addition together. So the seventh axiom is a distribution with respect to coefficients, real number coefficients. So this is the first distributive law. Again, this doesn't follow from anything else. Alpha plus beta, both real numbers, times x equals to alpha x plus beta x, where alpha x and beta x are elements of our linear vector space. And conversely, another distribution law, alpha times x plus y equals to alpha x plus alpha y. And obviously, due to these distribution laws, this is a consequence, not an axiom, and thus we can really expand expressions like alpha plus beta times x plus y, all right, in a standard way. So this would be alpha plus beta due to the first, well, let's start, due to the second distribution law, it is alpha plus beta times x plus alpha plus beta times y. And now applying axiom 7, we would say it is alpha x plus beta x plus alpha y plus beta y. Okay, so we can always do that. So these are the 8 fundamental axioms of a linear vector space. You see that we do not really define what are these elements, for example, x. Yes, we can treat them geometrically, but we can give completely different examples of linear vector spaces, which would be unrelated to our three-dimensional geometry. Okay, let's do a very short 5-minute break, and then we'll continue with examples and further properties. Okay, break 5 minutes.
Okay.
Okay, okay.
Excuse me, Mr. Merkin.
Hello, yes?
I assume we are still not touching the multiplication of the vectors, right?
Multiplication of the vectors, no. The
All right.
multiplication of the vectors is not, you are absolutely right. Multiplication of the vectors is not part of these axioms. Axioms of a linear vector space is only about adding up vectors and multiplying vectors by numbers. Multiplication of vectors can be introduced in several ways. And for example, there is a so-called scalar multiplication of vectors, or scalar product, or dot product, which we'll see in the next lecture, I believe. There is also vector product of vectors. There is also a mixed product of vectors, and possibly you can introduce some other products. So these are not part of these 8 axioms. Okay?
Okay.
We're resuming very shortly. Okay, we're back. So first of all, let us see some interesting consequences. Interesting consequences of those axioms. The first consequence is that our zero vector theta is unique. So there is only one zero in our linear vector space. How can we prove it? Suppose that there are 2 zeros. For example, theta 1, theta 2. There are 2 zeros, okay? But then, because they are both zeros, we can say that theta 1 is equal to theta 1 plus theta 2, because theta 2 is 0, right? Which is equal to now you see theta 2 plus theta 1, obviously, but we know that theta 1 is 0, and therefore this is equal to theta 2. Therefore theta 1 is equal to theta 2. If there are 2 zeros, then they're equal. Therefore there is only 1 zero, right? That should be funny enough. Now, a more interesting thing, we said that there exists an element for any x which is called minus x, the negated vector, minus x. Minus x is also unique. For any x, minus x is unique. Is unique. I will leave this as an exercise for you to prove. We can discuss it next time. Number 3, an interesting thing. We said that 1x is equal to x. That is an axiom, you remember. 1x equals to x. What about 0x? What is 0x?
Theta.
0 first.
0x is theta, right? 0x is theta.
Yes.
Interestingly enough, this is not an axiom. This can be proved that 0x is theta. Let us probably try to prove this, that 0x is theta. And similarly, by the way, we can say that other way around, for any alpha, which is a real number, alpha times theta is theta. Actually, the latter one is very easy to see, provided that we have proved the first one. But let's do it. Let's do it one by one. Okay. So 0x is theta. Okay. We can say that 0x equals to 0x plus theta, because theta is 0. Correct? Now, we can say that this is a 0x plus, and theta can be represented as x plus minus x by one of our axioms. There exists minus x such that x plus minus x is 0. Okay. Which is 0x plus x is 1x plus minus x, right? Because x is 1x. That is by axiom. X being equal to 1x is by axiom. Okay. Now using distribution, the distribution law, we can say that this is 0 plus 1 x plus minus x. Here, this is just addition of real numbers. So 0 plus 1x is 1x plus minus x. And 1x is x plus minus x. And we know again by axiom that x plus minus x is theta. So now we have proved that 0x is theta. What a wonderful achievement. By the way, have a look at this. Are there any questions?
No.
Okay. Now we can prove the property number 4, which say that alpha theta is equal to theta for any alpha. Okay. What is alpha theta? Alpha theta, we already know that theta can be written as 0x for any x which belongs to L. Right? We already know this. We have proved it just now. And therefore, by associativity, it is alpha times 0 times x, which is 0x. And again, we have proved that 0x is theta. This is done. So you can see how those properties, which also look quite elementary, can be derived from the 8 axioms. Now, let us do together. Okay, I said this last exercise. Let's do this exercise right now together. Any ideas how we prove that minus x is unique? What do we do?
We can suppose that there exists two such minus x, for example, minus x sub 1 and minus x sub 2.
You are right.
And we know that x plus minus x1 is equal to theta, and x plus minus x2 is equal to theta. From that, we can derive that x plus minus x sub 1 is equal to x plus minus x sub 2.
Okay, x plus minus x1 equals to theta. X plus minus x2 equals to theta. And so what? We would, well, if we subtract one equality from the other, we would say minus x1 minus x2 equals to theta. It still doesn't say exactly that they're equal, but you are very close to what we need to do. Again, you see what we started to do here. When we had assumed that there are two thetas, we can freely add the other theta to the first one. Let's do something a little bit similar here. So minus x1 is obviously equal to minus x1 plus theta. Correct? Correct. Now, what is theta? It is minus x1 is carried over, but theta is x2 plus minus x2. Okay?
It must be, I guess, x plus minus x2.
Sorry?
Well,
Yes, indeed,
yes,
yes, correct, yes. X plus minus x2, correct. Okay, now x plus minus x1, because x1 is the negative of x, is theta. Therefore, we have this theta plus minus x2, but because this is theta, then by axiom, this is minus x2. And we are done. Great.
Excuse me.
Yes?
Could we just say that x plus minus x1 is equal to x plus minus x2 from the first two equations? From this, yes.
X plus, you mean from these two equations?
Yeah.
X plus minus, yes, they're equal to.
So, and then we know that x minus x is equal to theta.
We know from our conventional algebra in real numbers, but x is not a real number, x is a vector. That's why this obvious thing wouldn't quite work. Okay, let's try to do it your way. So yes, because they both equal to theta, then of course they're equal to each other. X plus minus x1 equals to x plus minus x1 equals to x plus minus x2. And what? We need to cancel x on the left and on the right. But when we do it in conventional algebra, in real numbers, canceling these terms is only possible, we do it implicitly, because we add minus x to both sides. But in this case, we don't know which minus x to add. We can add minus x1 to both sides. Minus x1 plus minus x1 would be equal to minus x1 plus minus x2. and it's still not what we want. We can do add minus x2 to both sides. And then it is minus x2 plus minus x2. And it is still not what we want. So canceling the terms is only possible when we know that it is allowed due to a certain axiom. In real numbers, it is really because we know that indeed there exists a unique negated number, and then we can add it to the both sides of our equality, canceling x. But in this case, before we have established this fact, we can't. Now, of course, once we know that minus x is unique, then we can apply minus x to both sides and prove the equality, but that's only after this has been established. So the correct way to prove this is by using this technique. Don't do cancellation until you know exactly what you are doing. Now, and only now, we can do it. That's why working with those abstract concepts may be a tricky thing, actually. Okay.
Okay, I got it. Thank you.
Wonderful. So remember just out of this that 1x equals to x is an axiom, but 0x equals to theta can be proved, interestingly enough. Now, examples. Examples of linear vector spaces. So the first example is indeed our three-dimensional, let's say, Euclidean space. We will be using this example because it is algebraic analytical geometry. We'll be using this example over and over and over and many times again. So now a three-dimensional space. Let me now call, please do not confuse coordinates with elements of the vector space. So now we'll use x, y, and z to be coordinates. That's the origin. And what are vectors in this vector space? Vectors are simply, by the way, we can introduce them even without the coordinate space. So for example, if our L is just a coordinate space R3, even without any geometric interpretation, then vectors are just triples of coordinates. So for example, I denote a vector now by V, and it is just a triple x1, let's say x, y, and z. Triples of real numbers written as columns. X, y, z are just real numbers. Okay, this is a vector V, which belongs to our linear vector space. Then obviously addition of vectors is defined in a very elementary way. V1 plus V2, which is x1, y1, z1 plus x2, y2, z2 is defined obviously component-wise. x1 plus x2, y1 plus y2, z1 plus z2. Multiplication of a vector, so these are two vectors in L, and the result is obviously also a vector in L, where L is R3, three-dimensional linear vector space. And for any alpha, which is a real number, we define alpha V again component-wise as alpha x, alpha y, alpha z. In this case, those 8 axioms which we have seen above are not axioms anymore. They can now be verified. They can now be proved. So we can say that R3 is a particular example or a model or a particular example of a linear vector space. Obviously, it is very, very easy to verify the properties. So, what is theta in this case? Theta is the vector containing all zeros. 0, 0, 0. All right? What is minus v? Minus v is minus x, minus y, minus z. Can we, for example, verify that 1v equals to v? Obviously, because 1v is indeed 1x, 1y, 1z, and therefore it is indeed equal to v, and so on. So axioms 1 to 8 in this case can be verified on this model using the axioms of real numbers. That should be perfectly clear. Okay, so that's the first example. Now, once we created this R3 as just an abstract vector space consisting of triples, we can give it a geometric meaning. So indeed, if we consider a three-dimensional Euclidean geometric space, then we can associate vectors with their projections to axes x, y, and z. So in the standard geometric way, so for example, if we have 2 points, P1 and P2, and these points have coordinates, let's say x1, y1, z1, and point P2, which has coordinates x2, y2, z2, we can really now introduce a vector which is a directed straight line segment, which will be, that's our vector v, which will have in our original R3 model, which will have coordinates equals to the final point minus the initial point, x2 minus x1, y2 minus y1, z2 minus z1. In particular, if this vector has its initial point in the origin, then the vector can be associated with its final point, x, y, z. In this case, we have a point and a so-called radius vector of this point. Which is given by the triple x, y, z of its endpoint coordinates, with the addition of vectors and multiplication of vectors by number given component-wise, as we have discussed. In this three-dimensional coordinate space, it is very, very, very useful to introduce 3 very special vectors, which are called by convention, traditionally called ij and k. They're so-called directional vectors or orths of our coordinate axis. x, y, and z. Those vectors, I'm drawing them up by convention, are called I. And you know what? From now on, when we're dealing with vectors in three-dimensional space, in order to distinguish them from real numbers, we will always use the vector sign on top of the symbol which denotes this vector, even theta. Okay? So then I, j, and k will also be denoted like this. So what is the vector I? A directional vector, unitary directional vector of the x-axis. Any ideas what the vector I is?
It's
Which
1, 0, 0.
1, 0, 0, which points along the x-axis, obviously. It connects the origin with the point 1, 0, 0. X equals to 1, other two coordinates equal to 0. And then it is straightforward to see that vector j is 0, 1, 0, and vector k is 0, 0, 1. They are very, very important because you can see in a split second that then any vector which is, suppose that there is a vector v which is any x, y, z, can be written as x multiplied by 1, 0, 0 plus y multiplied by 0, 1, 0 plus z multiplied by 0, 0, 1, and therefore it is xi plus yj plus zk. Any vector with given coordinates is just a linear combination of our standard orths or standard directional vectors with the corresponding coordinates x, y, z being coefficients.
Excuse me, Mr. Merkin?
Yes?
If I remember correctly, those vectors can also be called normal vectors, right? I, j, k.
Normal vectors, directional vectors, orths, all these symbols are applicable, you are right. And by the way, it is a very good point why they are called normal vectors. In order to see this, I wouldn't introduce this term initially from early on, because in that case, we need to introduce the definition of normality. So let's do it now. We still have more than 10 minutes left, and therefore, for now, we can introduce a very, very important concept, which is a scalar or dot product of vectors. From your school geometry, you remember that this dot product of v1 times v2 is defined as a scalar. Which one? Do you remember?
Yes, it's x1 multiplied by x2 plus y1 multiplied by y2 plus z1 multiplied by z2.
Exactly. x1, x2 plus 1, y1, y2 plus z1, z2. That's exactly correct. And it has been demonstrated for two-dimensional vectors, and then it can be expanded to 3 dimensions as well, that there is another property of these vectors, is that the scalar product of the vectors is equal to the product of their absolute values times cosine of angle between them. But in order to see this, we need to define what the absolute values are to begin with. So yes, it is absolute value of V1, which is just a real number, times the absolute value of V2, which is a real number, times cosine of angle between vectors V1 and V2. Okay, first of all, what is the absolute value of the vector? The absolute value of the vector, just V, is positive square root of this vector multiplied by itself, V times V, which is immediately positive square root of x squared plus y squared plus z squared. This is the length of a vector or distance between 2 points in our standard Euclidean three-dimensional vector space. And now the question is, what is the cosine of V1, V2? How to define this? How to define the angle between the vectors and the cosine of this angle? So in general, I would say that if we are dealing with only Cartesian coordinates, x, y, z, and we have not introduced any notion of an angle at all, then it works the other way around. By definition, cosine of the angle between V1 and V2 is precisely given by this formula. Because so far we haven't introduced any angles at all. So now we say, yes, there is such a notion as an angle between the vectors, and cosine of this vector, of this angle, is by definition the dot product of these vectors divided by the product of their absolute values.
Okay, Professor Merkin.
Yes?
The angle between two vectors, by definition, is an acute angle. By regarding from the formula, we can get the negative result of cosine, and this is an obtuse angle.
You see, not exactly. You remember, if we return to the conventional geometric definitions of the angle, then what is the graph of cosine? So for example, this is our angle, which, let's say this is precisely this vector v1, v2, okay? So when it is 0, then cosine equals to 1. When it is pi over 2, and they are orthogonal to each other, then cosine is 0. Then it becomes negative and equals to -1 when the angle is pi, or 180 degrees. So for any angle, being acute or blunt, between 0 and pi, a cosine uniquely defined the angle, unlike sine. For the sine, you are right. For the sine, we wouldn't be able to tell whether it is an acute or blunt angle between these two vectors. But cosine, which can be both positive and negative, uniquely define the angle in the interval between 0 and pi. Okay?
Okay.
So this is a definition we can prove algebraically just by using properties of quadratic forms that indeed the absolute value of this expression, the absolute value of v1 times v2 divided by the length of v1 times the length of v2, well, okay, not even absolute values. We can prove that in general, this expression, which is a cosine, it is less than or equal to 1 and greater than or equal to -1. Or in other words, if we expanded x1, x2 plus y1, y2 plus z1, z2 divided by the product of square roots x1 squared plus y1 squared plus z1 squared and x2 squared plus y2 squared plus z2 squared belongs to this interval from -1 to +1. This is a so-called triangle inequality. We'll not prove it right now. It is proved purely algebraically by considering the maximum and minimum of the corresponding quadratic form. But you can see actually, well, if you like, I can prove it for you. If we take this expression and square it up, then it is equivalent to x1, x2 plus y1, y2 plus z1, z2 squared divided by x1 squared plus y1 squared plus z1 squared times x2 squared plus y2 squared plus z2 squared must be less than or equal to 1. Or x1, x2 plus y1, y2 plus z1, z2 squared must be less than or equal to x1 squared and so on, x2 squared and so on. Okay, and the remainder is pure algebra. Okay, so and obviously in our standard geometry, if we define the angle otherwise, and in our 2D or 3D geometry, the angle between two vectors, for example, is defined as the length of the unitary arc connecting the endpoints of these two unitary vectors, then this definition of cosine coincides with the definition which we introduced by the scalar product. This can be proved. Okay, so that's our geometric example, and vectors will continue about normality or orthogonality of the vectors in terms of the vector product next time. But before the end today, I would like to give you some completely different examples of a linear vector space, which is not related to our three-dimensional coordinates in any way. So that's example 2. Suppose that L is simply a space of polynomials up to a certain degree with linear coefficients. So for example, it is a space of polynomials of the form a0 plus a1 again x, but now x is just a variable, an indeterminate, plus a2x squared plus so on plus an x to the power n. The space of such polynomials. This is a linear vector space. What do you think is the dimensionality of this space? n plus 1, a0 to an, n plus 1. So you can see that it is equivalent to the space Rn plus 1 because each polynomial, x is just an abstract indeterminate, so we don't worry about it. Each polynomial is actually uniquely defined by its set of coefficients, a0, a1, and so on, an. Again, theta is a zero vector when all coefficients are zero. This is zero polynomial. Addition of polynomials results in adding up the coefficients. Multiplying a polynomial by a number, yes, it is multiplying its coefficients by a number, but multiplying polynomials together, one polynomial by another, is not defined in this case, simply because if we define it, then the degree of a resulting polynomial can, in general, be greater than n, and therefore we are not constrained by these n plus 1 dimensions anymore. So if polynomials are considered only in terms of adding the polynomials up and multiplying the polynomials with a number, then it is indeed yet another example of a linear vector space. That's all for today. Next time, we'll be, I give you a plan for next time, we'll be considering in more detail the dot product, what we call indeed the normality of vectors, and operations with changing the coordinate system. What if instead of our coordinate system x, y, z, we consider a system which is somehow rotated or maybe shifted with respect
Excuse
to
me,
the original
Mr.
system? Yes?
Merkin, regarding the last example.
Yes?
So you are saying that we can define any polynomial as a vector in a n, as an n-dimensional vector in some linear space, right?
N plus 1 in this case.
N plus 1, right?
Polynomial of degree n corresponds to a vector in n plus 1 linear, n plus 1 dimensional linear space, yes.
Okay, I see, all right.
Because, simply because, how we do it? We write the coefficients of this polynomial as a column vector, a0, a1, an. And then adding up two polynomials. So for example, if we have one polynomial which is f of x, and this is a0 plus a1x plus so on plus an x stepping n, x to the power n, and this is given by this vector. And another polynomial g of x is, let's say, b0 plus b1x plus so on plus bn x to the power n, and this is defined as a vector b0, b1, and so on, bn, then, and this polynomial belongs to L, this polynomial belongs to L, then the sum of these two polynomials, f of x plus g of x, is indeed a polynomial with coefficients a0 plus b0 plus obviously a1 plus b1 multiplied by x plus so on plus an plus bn multiplied by x stepping n, and therefore it can be written as a vector a0 plus b0 and so on an plus bn, and it also belongs to the same linear space L. Okay?
I have a question.
Okay.
Yes?
So if we consider that our polynomial of the degree n is defined by a linear space with n plus 1 dimensions, is from there derived that the formula for sum of x squared is derived by sum of x cubed?
Sorry, I haven't quite got it. So yes, we associate polynomials with vectors and
On the bootcamp, we had a task to derive a formula for sum of squares, or sum of x squared, and we derived the formula from sum of x cubed, from cubes of x.
sorry, you mean this example when we're trying to prove that the range is from -1 to +1?
Not exactly.
Not exactly.
Maybe you didn't get me. Can I text you later?
Yes, obviously, yes, you can, and I will be very happy to answer it. Yes, please.
Right. Should I send you an email or somewhere else?
If you can do it, you know, Telegram is easy. So, by the way, it's not only for you, for everyone. If you have any further questions which you would like to discuss offline, please feel free to send the questions to Telegram.
Right, thank you.
You can write it down and send an image to Telegram. I
Oh,
will answer. Okay.
Mr. Merkin,
Yes.
it would be great if you share all the notes from this lecture, like the ones you wrote.
Oh, yes, of course. It will be not only video, but the notes as well. Indeed.
Excuse
Alright.
me, do you mean that we can see your drawings in the future?
Yes, right now I will publish these drawings in Moodle. I will put the recording of the lecture as well, and to YouTube, and provide a link to Moodle. I really hope that you know, recording was successful.
Thank you very much.
Okay, thank you.
Thank you.
Thanks everyone for the attention. We're done for today. Thank you.
Goodbye.
Thank you.
Bye.
Goodbye. Thank you. Bye.